Hello and welcome to our Building Energy Codes seminar series. The series is based on our National Energy Codes Conference, which is hosted annually by the U.S. Department of Energy. We're here to present you with the latest in building energy codes, from developments in the model codes, to updates on what's happening across states and local governments, to highlighting tools and resources that you can take advantage of in your day-to-day practice. We'll be hearing from a number of leading experts about the challenges they're facing, ways they're working to solve them, and how their efforts are building the energy efficiency, comfort, quality, and affordability of America's homes and businesses. Join us virtually for important topics and interactive discussions, and help us continue the conversation. To learn more, visit energycodes.gov.
Hello and welcome everyone. My name is Ian Blanding with the Pacific Northwest National Laboratory, and welcome to the National Energy Codes Conference Seminar Series. So this seminar, we will be talking about grid integration and electrification in energy codes. Looking ahead, we have a whole host of topics to cover, talking about zero energy codes in commercial buildings, codes around the globe, the evolution of commercial building design and construction, equity, zoning, and others. And so if you're interested in learning more, you can click on the link below to get that full list of the seminar series, and then also sign up there. And just a few housekeeping items. So everyone is in listen-only mode. And if you have questions, we ask that you enter those questions into the question pane, and I will relay those questions to our presenters once we get to that point. So we have a lot that we want to cover today. So without further ado, I will turn things over to Ellen Franconi of PNNL. And Ellen, I will make you the presenter.
Great, thank you, Ian. Well, welcome everyone to the Building Energy Codes Program 2021 Seminar Series. And we're really happy to be kicking off the series with a discussion on the focus of, well, the role of building energy codes in advancing connected buildings. My name is Ellen Franconi, and I work at Pacific Northwest National Labs in the Building Energy Codes Program, and we support DOE in its efforts to advance building energy codes. And I'm really happy to be joined today with Mark Frankel. Mark?
Good morning or afternoon, everyone. Thanks for having me here. My name is Mark Frankel. I am the Director of Policy and Innovation at Ecatope in Seattle. We're a research and engineering firm. We're deeply involved in development of heat pump water heater technology and grid integration on that, and leading edge design work. Prior to my recent two-year stint at Ecatope, I was the technical director at New Buildings Institute for about 15 years, and kicked off a lot of grid integration work that they have been carrying on well in my absence, and we'll talk a little bit about that. Thanks for having me.
Thanks, Mark. Yeah, Mark and I recently have been working together on the Washington State Energy Code, so it's great to be able to continue to collaborate with you, Mark. Okay, so we'll be talking about the role of building energy codes to advance grid interactive efficient buildings, or GEBs for short, and with efforts ramping up to develop a clean grid coupled with building electrification, including GEB technology and code is becoming increasingly important. And there's also a lot of efforts in the nation to address carbon and climate change. And buildings are an important part of that discussion. And as shown in the pie chart, building energy consumption in their operation contribute to 32% of US greenhouse gas emissions annually. And if you add in the emissions associated with the building materials in which they're constructed with, that makes a total of 38%. And decarbonization is also a big topic for DOE. You can see the 5 programmatic priorities listed for the Energy Efficiency and Renewable Energy Program, or EERE. And the top one is achieving a carbon-free electricity sector by 2035. So this means a clean grid. And since buildings consume 70% of US electricity use, they have an important role to play here. And also number 4 on their top 5 is reducing the carbon footprint of buildings across the nation. So again, talking about decarbonization, buildings do have an important role to play. Perhaps some of you caught the National Energy Codes Conference, which was held virtually in July. If you did, you probably got to hear Secretary Granholm address the conference. And I found that really quite exciting to have someone at the highest level at DOE recognize the importance of building energy codes and the way that they provide added value to building owners in society. So what is a grid interactive efficient building? Well, there are generally 4 key attributes which they have. The first is energy efficient. And improving efficiency helps reduce overall energy use and peak demand. They're also flexible in the way that they use energy by shedding or shifting load. And this can be done through storage technologies or demand flexibility strategies. They're connected with a 2-way communication to support the grid and also offer added value to occupants. And they're also smart, meaning that they are equipped with the proper controls to make the most of the information from the grid and coordinate other equipment within the building to optimize for costs and also occupant comfort. Another way to think about GEBs is how the GEB technologies impact the overall building load shape. So thanks, Mark. I borrowed this slide from NBI, some of your past work. But if you take a look at the blue curve, this shows the base load of a building. Now, if we apply energy efficiency technologies, you can see the green load shape curve. There's an overall decreasing, including peak demand and just overall energy use. If we were to apply some automated demand response controls, we were able to shed load during peak demand periods, which can certainly support a clean grid. And also using storage technologies, we're able to shift load during the peak periods into lower demand periods. And this is the sort of thing that happens when we do ice thermal storage systems, which charge the system at night when peak demand is low, and then use it during the day when it's highest. So some of the GEB technologies that are available today are indicated in this graphic. And this graphic came from DOE's National Roadmap for Grid Interactive Efficient Buildings, which was published earlier this year in May. It's actually a great report, and I recommend you check it out. But what this shows is the control technologies are in blue at the top of the chart, and they're about connected systems and also the smart operation and optimized operation and coordinating different systems across the building. On the bottom of the chart, you can see the physical systems in orange. These are more envelope systems or mechanical systems, and they can be dynamic, as in glazing. They also include electrification technologies such as heat pumps and electrification with increased efficiency, such as heat pump water heaters. And in the red, these are the thermal storage systems, including water, battery, and ice thermal storage, as well as building thermal mass. And I think what's kind of excited, as you can see, moving forward through the pilot to the development stage, is there going to be more integration of energy storage with different types of building systems. And not only will this help, I guess, with our demand flexibility, it will also help with realizing building resilience and passive survivability. The DOE National Roadmap study also included some analysis about the DEB technology technical potential. And as you can see, it shows what that potential is through 2030 in a couple of scenarios. So if we look at the peak demand reduction capability, what's identified as existing, we can multiply that by about 1.5 times if we're able to realize the DEB technical potential. And that's just for demand flexibility. That's in terms of peak demand reduction. If we look at it in terms of energy use reduction, that's about 1.3 times the existing identified savings potential. So you can see that DEB technologies can have a big impact on energy savings and peak demand reduction, and they are a key strategy for realizing some of our national directives for decarbonization and achieving a clean electric grid. And as we've seen, buildings have an important role to play due to their large need for electricity, 70% of national electricity use. And certainly buildings present important policy lever for achieving these objectives. Okay, so I'll hand it over to Mark and he'll get into some more trends and drivers for DEBs.
Thanks, Ellen. I want to talk a little bit about some of the larger market and policy trends that are driving both the need and the opportunity for grid integrated buildings. So I like to think of it in terms of some basically 5 big drivers in the market right now: Z&E proliferation, building decarbonization, vehicle electrification, resiliency, and grid decarbonization. I don't know if you guys recognize this image of the future of Wakanda. I love that picture with Zaha Hadid inspired architecture. Please move on, Alan. So we've been talking about net zero buildings for a very long time. Next slide, please, Alan. There we go. We've been talking about net zero buildings for a decade now, and it's been set as policy of many organizations we all work for, and many states and cities have set a goal of achieving net zero energy with code by 2030. And NBI has been tracking progress on this for a number of years and puts out annual or biannual reports on progress, but the curve is steepening and the codes are moving closer to net zero. And of course, a net zero building has distributed generation inherent in it. So on-site solar, typically more and more battery storage as well. And so we're seeing a lot of building interaction with the grid that's different than it used to be because of the net zero policy. Next slide, please. Recently, there's been a lot of discussion of building decarbonization with cities and states moving towards elimination of combustion in buildings or starting to push in that direction. And there's also the embodied carbon issue, which is less about the grid, but it's part of building decarbonization, so I want to mention it. But when we talk about removing combustion from buildings, we add a pretty significant impact to the grid by replacing the energy that we get from combustion in buildings for heating, obviously, with electricity in heat pumps, et cetera. And so that's driving a new shape of load on the grid and new seasonal impacts that play out into building integration. Next slide. Another big policy goal is vehicle electrification. And even though it's not happening as fast as some people think it should, it's definitely an upward curve and a pretty strong projection into the future. And that, if you recall Ellen's slide about the distribution of energy in the US, that's roughly a third of the US energy use is transportation. So if we electrify a lot of that, that's going to have a significant impact on our grid, which means that we need to think about how the grid is going to work in the future as we move in that direction. Next slide, please. Energy resiliency is another goal that was mentioned. And you know, just a few years ago when we thought of energy resiliency, maybe the image was Puerto Rico after the hurricane, where they lost their entire grid and had to think about rebuilding. But I think the definition of energy resiliency for American consumers has changed quite a bit after the PSPS, the Public Power Supply I can't remember what PSPS stands for, but the fact that grids go down for fire protection and other reasons with some regularity, I think that was a big shock in California when PSE started, or PSE started turning off the grid to protect the fire line, to prevent fires, and whole regions were all of a sudden without power. And so instead of it being about resiliency for your bunker, it's resiliency for the things in your refrigerator for tomorrow's dinner. So I think there's a very different perspective on how individual consumers interact with the grid now that's driving a lot more focus on resiliency that's also going to have impacts on the grid. Next slide, please. Ellen also mentioned that there's grid decarbonization mandates. My state, Washington, has a requirement that our electricity will be 100% carbon-free by 2045 and net carbon-free by 2035, I believe. And other states as well. This map is old, but many states have adopted carbon reduction goals for the grid, including the new infrastructure bill that's come out is focused on reducing carbon in the grid. And that has really important impacts when we think about the way we serve the grid with power supply. Next slide, please. This is two graphs of energy from two different sources. On the left is wind and on the right is solar. And there's two intermittency issues I want to point out here. In the right-hand grid, this is a solar day with clouds going overhead. So every one of those white spots in that curve is where a cloud has interrupted generation from that particular array. And you can imagine what the grid has to do to respond to these instantaneous changes is very different from the old days when you're running a coal plant or a gas plant and it's on and it comes off for planned maintenance months ahead or whatever. And here we're having moment-to-moment interaction with the grid, which means that we really need more flexibility in the grid to respond to this. On the left side is a diagram of wind power through a month in April, a decade ago or so. But you can see the blue line down in the middle is the average capacity of this wind farm. But the daily generation is all over the map. And so when we think about what is the wind resource, it's highly variable. And so we need a lot of flexibility on the grid to respond to the variable nature of renewable energy. And sometimes that means that we just build over capacity and have curtailment, meaning we feather the blades of the wind farm and only provide what's needed, or ramp it up when we need extra capacity. But there's a whole lot of additional control and flexibility that's needed. And buildings have a really important role in contributing to the solution to the problems that are presented with this kind of variability on power supply. Next slide, please. This is played out in something you've all heard of, the duck curve. And what that represents is the fact that in California, there's a whole lot of solar on the grid in the middle of the day. And so the belly of the duck shows the net load on the grid as more and more solar is put on. And what you see, there's two issues here. One is that sometimes there's just too much power on the grid. And California sometimes actually has to pay other states to take surplus power in the middle of the day. So that's where we get the concept of negative power pricing. They have so much energy coming in, they have to dump it out to other resources. And that's maybe a temporary problem that will be solved by storage. But the head of the duck is a different problem. And that is that as the sun goes down in the afternoon, the peak load is just as big as it ever was. And so they need all the old generating resources besides solar to meet that head of the duck supply problem. And so that sets up a whole bunch of questions around, can we shift the shape of our building loads to reduce the size of the duck's head and take up some of the slack in the belly of the duck? Obviously, one solution to this is storage. Next slide, please. And what we're seeing in storage is the price of batteries are dropping really fast. According to Bloomberg, they are halved every 3 years over the last decade, which is astounding. And if you think about, on the next slide, if you think about the way solar power went in the last decade, you know, for many years it was just ridiculously expensive, and then it was sort of down low, the flat part there in the 80s and 90s. And then all of a sudden it crossed a threshold, even though it wasn't a very big difference in the 2000 to 2005 time period. It crossed a threshold and deployment shot up. So, we're going to see the same thing in battery storage here soon or sometime, where all of a sudden it's going to cross a threshold and it's going to be a lot more cost effective. And things like the drive for resiliency and the need to shift your load out of peak periods, et cetera, are going to drive that more. So next slide, this is another Bloomberg projection of battery deployment going up to 2030. And interestingly, the purple part of these graphs is behind the meter storage. That is at the building scale. So we're expecting a substantial portion of storage deployment to happen at the building level, which is another part of grid integration opportunities for the building sector. Next slide, please. So this plays out, as Ellen mentioned, in different ways in the building sector. The opportunities for building integration have to do with efficiency. Efficiency is still a valuable resource because it reduces the overall impact, but also peak shifting, dynamic response, the ability to respond to events or sudden peaks or hot temperatures or cold temperatures, what have you, and dispatchable energy storage. Can the buildings actively contribute to the grid through V2G or batteries on site that supply the grid when needed, et cetera. And then the last thing I want to show you to sort of set up the discussion of how we can start talking about codes is the fact that within the building, there's different loads that can be managed differently. This happens to be a residential load example, and the red dashed line in the middle is solar availability. But the other pieces of equipment in a residence or in a commercial building have different load shapes individually. And so we can talk about water heating. Measures to deploy water heating controls are going to have an impact at certain times of the grid, and measures to deploy HVAC efficiency are going to have an impact at a different time on the grid. And so we can start to think about individual pieces of equipment as part of the DEB lexicon for codes. And so when we think about it that way, I think we get to the point where we can start talking about how can we tinker with energy codes to provide the kind of flexibility to the grid that it's going to need to achieve the larger goals we have. With that, I think I will hand it back to Ellen to talk about some of the work that's going on in codes now.
Great, thanks, Mark. What a great overview. Yeah, so why don't we take a look at what we have in current published codes to know where we're starting from and where we need to go. Before we get started, there's a lot of sort of specialized terminology associated with codes, so I thought I'd go through them so I don't lose anyone. To start off with, there are building standards. And a standard isn't necessarily a code, but it's often referenced in a code. And then within building energy codes themselves, these are documents that are adopted by state and local jurisdictions, and they establish the requirements for buildings, new buildings, major renovations in their areas. Usually compliance can be achieved through two different methods, either a prescriptive path or performance-based compliance path. A prescriptive path is straightforward but not flexible, pretty clear about what you need to do to implement it. A performance-based path, it's more that metric targets are established and the design needs to achieve them. You need to demonstrate that you're achieving that through a simplified performance-based compliance tool or whole building simulation modeling. And there are also mandatory requirements which apply to both compliance paths. There are a couple of codes that are recognized as being the model energy codes for the US. And a model energy code is designed to have wide adoption. It lays the groundwork so other states or local jurisdictions don't have to. And those two codes are the International Energy Conservation Code for residential, or IECC-R, and also for commercial, it's ASHRAE Standard 90.1. And while this is the standard, it is referenced by the IECC commercial in actually other code documents. So then that is what's typically referenced by a jurisdiction. I'm also characterizing a group of codes as advanced energy codes. These include the International Green Conservation Code, and this is more of a voluntary code, although I'm sure some jurisdictions may require it. Also California Title 24. While this is a state code, still California, as Mark pointed out, they're experiencing a lot of renewables on the grid, and that has given them an early start on thinking of some of these implications and reflecting some solutions within energy codes. And then lastly, the NBI Building Carbonization Code is really interesting, and we'll describe that. I left one out of the list. One is the Washington State Energy Code, and we'll say a bit about that too. And of course, there's voluntary programs. LEED has been that in so many levels, but now they are including grid integration pilot credits, and also in cooperation with that is the NBI Grid Optimal Project. Okay, so the next few slides go through these different published codes, the model codes, and some of these advanced codes to see what currently are requirements related to DEB within them. So this slide summarizes the requirements related to DEB for the model codes, residential and commercial. As you see from this text blocks, there's not really anything too directly in there. There's no communication requirements, load flexibility requirements, or on-site renewable energy systems. But yeah, there are opportunities for layering on, adding incremental requirements that leverage current control requirements already in codes. And also, I should mention, generally these codes or standards are continually maintained. So while in the 2019 ASHRAE standard, there isn't any on-site renewable energy requirement, there is one in an amendment to that code. Okay, so now looking at the Title 24 2019 residential, this has got a lot of detail on it just to show you a little bit. Maybe if you want to delve into it after the webinar, you can read this and just get a sense for what is being included in code more specifically. But at a higher level, the residential code includes a requirement to adhere to a specific communication protocol referred to as Open ADR, or Open Automated Demand Response. There are prescriptive requirements for on-site solar energy systems. And then there are also solar-ready requirements should any building or project have some sort of exception and not have to install one, so that in the future they're still ready to have those systems put in place. There's solar water heating for multi-unit buildings. And also for the performance compliance path, they have a PV flexibility design rating that can be used to contribute towards meeting the overall building performance compliance target. And in this table, it summarizes the DEB related requirements for Title 24, 2019 commercial, and the International Green Conservation Code 2018. So these are both commercial building codes. So the Title 24, again, specifies Open ADR as a communication protocol. IGCC does not. And I should mention, the IGCC is powered by ASHRAE standard 189.1. And 189.1 within the energy section actually references ASHRAE standard 90.1. So you kind of integrate something into one part, it kind of ends up going into another part. So within the IGCC, knowing 189.1, they do require DR communication, they just don't specify a particular protocol. There is on-site renewable energy production required in both of these codes. Solar-ready buildings, EV charging is in IGCC, and demand-responsive thermostats, HVAC, and lighting is in both of them. And I mentioned earlier that Mark and I worked recently on the advancement for the 2021 Washington State Energy Code. And one part that I'm quite excited about is that they have a section now that addresses load management capabilities, including all of these different technologies. And They also include a section about on-site renewables. And this is part of a whole code mechanisms referred to as advanced energy efficiency credits. And I'll talk a little bit more about that in the next section. Okay, I'll hand it back to Mark and he can talk about some exciting work that came out of NBI.
So NBI has a long history of working in the codes sector, and they do a great job of collecting the best practice codes from around different jurisdictions and bundling it up into guidelines that can be used by other jurisdictions, and it actually ends up spreading the code around quite effectively because everyone wants to be the first to be second, as I like to say, where if someone else is doing it, we can do it too. And so they've published recently a guide to decarbonization code language that can be policy and code, and it covers a lot of issues that are grid integration issues as well, including demand responsive thermostats and HVAC, demand responsive lighting, building electrification, on-site renewables. All these things are very critical to the conversation around GEBs, because again, as I mentioned, you know, the notion of net zero buildings is that you then dump all your spare energy in the summer into the grid and it's your battery. And what we really need to get to is a much more nuanced and flexible approach for building loads that is responsive to grid needs and grid conditions and supply shapes, and pays attention to building load shape. But the NBI Decarbonization Code is published. It's a great resource. You can find it at the newbuildings.org website, and I recommend that you take a look at it and many other code resources there. And then another thing that's going on in the optional program and is the LEED grid integration pilot credits. And these are based directly on work that NBI has been doing on the Grid Optimal Buildings Initiative. And the Grid Optimal Buildings Initiative is more focused on utilities that want to roll out programs on grid integration, but LEED has adopted pieces of that as a pilot credit program, and it's worth a couple points in LEED. And the metrics are these 6 metrics, which is how you're aligning with grid peak, how you're dealing with carbon reduction, whether you're using on-site renewables on-site or trying to dump it into the grid, and then short and long-term flexibility, and that's another issue maybe we can talk about in the discussion period, and then whether or not it's dispatchable by the utility in a crisis. So as you look through those, and this is published on the LEED website, you can, if you're working on LEED projects, you can get extra LEED credits for dealing with grid integration.
Okay, so certainly there's a lot of impetus for moving towards GEBs in buildings and GEBs in building energy codes. So we'll dive into some of the challenges for doing so and also the opportunities. So in summary, some of the ideas that we're going to share are challenges that include large variations in utility rates not reflecting electricity carbon emissions, and also the more simplified compliance path, the prescriptive path, not really allowing a great way to account for the variability in rates or carbon. But there are opportunities. There are GEB technologies available today that can be considered, new code compliance mechanisms that can support them, and also analysis that can be done to inform GEB advancement in code. So when we say utility rates are all over the map, they really kind of are. The data shown in this US map was extracted from the OpenEI utility rate database. So we accessed over about 7,000 rates that were identified as published current commercial building rates. And we took ones, we looked at rates available in each county in the US, and we identified the rate with the highest peak demand charge, and that is the value you're seeing in this chart. And we just wanted to get a sense for, does all counties have rates with demand charges, and what is the potential range of these demand charges across the US? So you can see it's pretty large. I mean, there are a few counties without demand charges based on the rates we were able to access. And then there's some that really have quite a large demand charge, with it being over $30 per kW. So that's one thing of trying to account for what might be the different value to building owners in respect to all these different rates across the country. So it's one thing to say there are different rates. We just wondered, well, what does that mean in terms of their impact on annual energy costs and, of course, implications on energy savings. So at PNNL, we're starting to do some analysis. We've gotten so far to just evaluate the impact of rates, published rates, time of use rates, using one of our code prototypes. The meeting office building, we kept the weather zone the same. It's climate zone 4A, which is New York City. And so the only thing that's changing in these results are the utility rates for electricity. So as you can see, there is a wide range across the 401 rates that we identified that have the three components we were interested in: a kWh charge, a flat kW charge, and then a kW peak charge. So it's just something for us to consider. I mean, even if we chop off, you know, the 25% in the bottom and 25% at the top, we look at the middle, it's still varying by about $20,000, which is a large percentage of this building's energy use. But one thing we can do, although it is hard to capture all those rates across the country, is to at least develop some sort of a representative U.S. time of use rate. And this work has been done. And I'm happy to say that in 2000, the ASHRAE 90.1 Economics Working Group adopted a proposed representative U.S. time of use rate that could be used to consider new code proposals. And so you can see traditionally what's actually used in code development to consider new proposals is a flat blended rate. And you can't show any benefit with demand flexibility if it's constant over every hour of the year. But now with this new rate, at least we can show some variation. The solid line is variation in energy charges, and the dashed line is variation in peak demand charges. So that is helping. And we did apply this rate in some studies done at PNNL to understand what difference it makes. And so we evaluated a handful of different measures, and you can characterize them as sort of being more controlled demand flexibility, which actually the measures were more about load shedding, more equipment efficiency improvements, envelope efficiency improvements, which could affect the overall building load shape, and then battery storage, which of course is shifting. So although we weren't able to capture cost effectiveness for each of these using the ASHRAE time of use rate or that representative rate, which are indicated in green, certainly the lower cost measures were easy to capture. So there are opportunities today where we can apply general rate information and get measures into codes, but some more work to be done to better differentiate regionally to get something more expensive like battery storage into codes. And we talk about new code mechanisms. I was alluding to this in the Washington State Energy Code slide, but there is one mechanism called extra efficiency credits, and it lives within the prescriptive performance path, but it provides flexibility because you can choose one path, which is definitely cost effective, or other technologies listed to meet the requirements of this. And it's more based on a point system. And my colleague Reed Hart has been pushing this forward, I think, since 2015 to get it into the IECC, and also it's now being proposed in 90.1, and it is also proposed in the Washington State Energy Code. And the Washington State one includes a section and also proposed within 90.1 of load management credits. Okay. And this is not just for prescriptive, but it's also referenced for performance-based compliance. Okay, Mark, I'll hand it back to you.
Thanks. Before I talk about the carbon issue, I just want to highlight something about rates that Ellen was talking about. So as Ellen mentioned, if you have a flat rate, there's really no perceived benefit to any sort of flexibility in your load shape. Once you have demand charge, then there's some advantage to the building to manage their peak loads with, you know, flexibility on or storage or solar or what have you. And then when interest rates, that becomes a much more nuanced thing. And that's the direction we're headed. California is already there. They have they have a bunch of different time of use rates. New York's got some time of use rates. And so this is an evolving field, the way rates work. The reason it's important in this discussion is that if we want to justify putting grid flexibility measures into code, we need some way to prove a value. And so the ASHRAE time of use rate is sort of a placeholder to demonstrate, even with this fairly modest time of use rate, there's a benefit to the buildings to having the flexibility. And that gives us a foot in the door to start talking about incorporating this into code. But it's challenging because those rates are all over the map, as Ellen said, and they're evolving quickly. So what we're really talking about is kind of future-proofing some of these buildings, because as the rates change, if they have the flexibility to respond differently, it'll be cheaper to operate them in the future. Another issue that's a challenge is the fact that we're targeting carbon reduction really in the big picture, and the rates don't necessarily align with that, and they're not as, the data is not as resolved. So this is a picture of a day of generation in California, and you can see all the different resources that go into the electric supply over time. There's the solar bump in the middle of the day, and as the sun goes down, the gas consumption goes up, and imports from other regions go up, which could be, you know, coal or gas or hydro or whatever is available on the grid. And so when we try to capture that in thinking about buildings, if we go to the next slide, if you map this over an entire year, this is a picture of building carbon impact for a pilot project that I worked on with NBI. And what you're looking at here is a map of the entire year, the carbon signature for the entire year of this building. And I say of this building, this is not the grid signature, because you can see the big bars, the green bars at the top and the bottom. That's nighttime when the building's hardly using any energy. So no matter how carbon intensive the grid is, if the building's hardly using any energy, its carbon footprint is small. But once the building starts ramping up, you can see there, you know, 5:30 in the morning, then the grid conditions start to impact. And you can see a pattern here. In the winter mornings, the grid is pretty carbon intensive. And in the summer afternoons, it's pretty carbon intensive because there's so much demand for cooling in this particular building that, you know, even a little bit of carbon on the grid is a big signature when the demand is so high. And so when you think about how to translate this into building response, the next slide, if you take slices through 4 days and look at building load shape, on the left side is winter mornings, and that brownish pink bar is the carbon critical period in the winter. If we can reduce our winter morning warm up, we can have a big impact on carbon signature in this building. And in the afternoons, in the summer, when everyone's trying to cool and there's not enough power on the grid, then that's the time in the summer when we want to reduce load impact. So the question is, how do we translate this into a code requirement for flexibility? And for now, what we can really only do is so far all we're doing in code is trying to encourage or require that there be load flexibility in the buildings. But if you want to get to the point where you're actually regulating on carbon, on a carbon signal, which is, you know, just barely becoming available, we're really talking about a much more nuanced evaluation than is going into code right now for a prescriptive path. Excellent.
Yeah, that's exactly right. I think historically we really focused on efficiency and annual energy use reduction and cost savings, but now we're talking about a much more granular assessment. And as part of that, we're looking at hourly carbon data, or considering it, or different forms of carbon alongside our other traditional metrics of cost. But one thing I wanted to share with you is this data that came out of the NREL's Cambium tool. It presents, it's a 20-year levelized carbon emissions, long-run marginal CO2 equivalent emissions data that was developed from using the tool. It shows an average day over the 20 years for each grid region in the US. And these are Cambium grid regions, but they're mostly equivalent to the EIA E-grid regions, if you're familiar with that. But the biggest thing I want to point out is the color coding. while we know that California has a lot of renewables on the grid, and that's actually the second row, and so therefore there's a lot of clean generation happening during the day. Other grids, which might not be there yet, they're going to be there. And so I think across the nation, this will become an increasingly bigger problem or opportunity, I should say, and it will require shifting the load into the daytime. So we really do need to consider how with building energy codes, how do we future-proof the investments made today to benefit building owners in society.
So with that, I think we'll offer a quick summary of what we're talking about in codes and then open up to some questions. So next slide. So Ellen and I talked about the kinds of things that are going into code now. In the prescriptive code, there's a lot of opportunity to require or encourage flexible load capabilities in heating, cooling, hot water, vehicle charging controls. Smart appliances is something that there's a lot of focus on for the appliance knowing, you know, the refrigerator knowing when to go on based on power price and so on and so forth. And any of this stuff needs to be commissioned or it's never going to get deployed. And then all the ways that solar and storage gets deployed in buildings has an impact here as well. And we didn't talk too much about the concept of self-utilization, but it's really important to think about whether you're using the power you generate on site or trying to dump it into the grid, because that adds a lot of challenge to grid management, and it's actually better economically for you to use the power you generate on site, honestly. And then on the performance side, you know, we talked about how rates are trying to align with carbon and they're not there yet, and the fact that we're going to have time of use rates in the future that are going to allow more load shape modeling, but that's really difficult to regulate in the current code landscape. So we were looking at opportunities and challenges, Ellen and I, and when we put this slide together, we realized that the opportunities and the challenges are basically the same set of issues. Because how do you require flexible loads and how do you define that even in a prescriptive pathway? And we've got an attempt at that in the Washington State Energy Code proposal, and ASHRAE's looking at this as well. All these things are starting to go into code, but it's early days. And then when we start talking about really managing load shape, you know, how do we sort of put together modeling requirements that require people to think about what the load shape implications are in relation to the grid and carbon. So the same things that are opportunities are challenges. This is the early days for DEB in codes. Next slide. But overall, we have some trends. We know for sure that we have to address the role of buildings in codes and on the grid. But we're not going to get to the goals we have for decarbonization without increasing the flexibility by which we can interact with the grid. And we believe that building energy codes are a very effective policy mechanism for starting down this road. The variation in utility rates and the fact that utility rates and carbon emissions don't necessarily align are challenges to doing this the right way. And the fact that the prescriptive path is really a very oversimplified way to get at the end goal is a challenge we have in making the codes really effective on grid integration. At the same time, even now, demand charge makes DEB technology very cost effective in many places and many types of technologies. We are experimenting with code compliance mechanisms, and some of those are going into code in California and other places, Washington hopefully. And there's a lot of work going on at DOE and other places and NBI on analyzing what it's going to take to bring this stuff into code. So with that, we'll take a few questions. Ian, do you want to manage that for us? Oh, I'm sorry, there's one more. Well, here's some things we could talk about, but let's see what questions we have.
Yeah, it'd be great to hear from the participants if they have any questions.
Questions, let's see. So question is for maybe Mark, but Ellen, you certainly jump in. When you were talking about the duck curve, Mark, there was a question that came in asking whether the duck curve is going to be the same shape when people are working remotely, if that trend continues, and what we do about that in terms of DEB and codes and responding to that.
It's a very interesting question. I don't think a whole lot of research has been done on that. We're actually doing some modeling to see what the impact is on individual building sectors. We certainly can expect that there's more residential energy use in the daytime for plug loads for computers when people are working at home. I would say what it does is for sure it changes the shape of individual building types, you know, maybe lower energy in the commercial sector and more in the residential sector. With that said, we're not really turning off the commercial buildings. I mean, maybe we see some plug load reduction, but we're probably not shutting off the HVAC system. So I don't expect it to be a huge impact. But when you net it all out, you know, the computer loads for workers are happening somewhere. And so I don't think it has a huge impact on the aggregate load shape. It just changes whether that's a residential or a commercial signature. That's my guess.
Ellen, anything you want to add to that?
No, not really.
Okay, great. And so we had a comment, Ellen, when you were talking about the various energy codes with DEB related technologies. So the California Energy Commission unanimously approved the 2022 California Energy Code, which will require solar PV and battery storage in select newly constructed non-residential buildings. And so just wanted to note that, and that'll be effective January 1st, 2023.
California likes to promote the fact that they're in the lead, which they are. I know New York is very antsy to show progress as well, and there's kind of a battle between the administrators of those two states on who's doing the best job, but it's happening everywhere, and it's great that California's provided leadership for so long. You know, we're pretty proud of our code progress in Washington as well. So.
Sure. So here's a question that just came in. So you guys have mentioned that prescriptive codes are too simplified, but there are many who would say performance code compliance is a bit too involved and costly. Has there been any discussion on expanding the intermediate trade-off options?
Yeah, I think the additional efficiency credits is one of those new and emerging code mechanisms that allow for those trade-off options. It's more flexibility, but within the prescriptive path. And I also think the performance path is, it is more complex, but there are more simplified performance-based compliance tools such as TSPR, Total System Performance Ratio, I believe, where though mostly it's about HVAC, but it can be applied to lighting, it can be applied to envelope, which allows for these trade-offs. And I think ultimately they could adopt a standardized way to incorporate demand flexibility technologies and demonstrate their impact in somewhat of a uniform way, which would allow, I think, better consideration of those technologies within performance-based compliance.
And I would just add, I'm not sure we made this clear, but in Washington, the way it's set up is there's a list of flexible features, and you have to choose one or more of them depending on how many points you're trying to get in that table. And so it's really up to the project to decide what's the most appropriate approach for them, with the idea that it's future-proofing the building so that as rates change and there's more demand charges and more time of use rates, they have some built-in flexibility that they wouldn't otherwise have. But it's really just a foot in the door for now, and it's going to get expanded upon. The other thing, excuse me, the other thing I would point out is that, you know, there's a lot of different kinds of flexibility. There's flexibility that where you've got a rate structure that has different time of use rates during the day, like California's TBV, et cetera. And, you know, you want maybe your controllers are actually responding to utility rates. There's also demand response, which is, you know, infrequent, where the utility's got a short-term crisis and wants a 15-minute block of savings. And, you know, the same kind of control system may enable both, but they're not the same thing. So.
Great. I don't know if you guys have insight on this. Question came in regarding water heating cost. How does PV solar with heat pump water heaters compare to thermal water heating systems?
We at Ecatope, we do a lot of multifamily systems with heat pump water heaters. It's something we are doing all over the country, and we're working with manufacturers and helping roll that out into various codes. It's not cheaper yet because gas is really cheap. what we found is it's cost effective if you are able to eliminate the gas distribution system in a multifamily building. It makes heat pump water heating technology cost effective. But you have to have the savings on the gas distribution. If you have to put in gas anyway for rooftop barbecues, which honestly is what happens, then you don't get the savings on the gas. So for now, it's more expensive, but it's early days of that technology and it's coming down in price. And so I think that will become more and more cost effective in the near term. And it's cost effective now if it actually fully replaces the gas distribution system. So there's one answer for you.
Great. We got time for maybe a couple more questions. So cost, you guys discussed cost benefit, and there's a question with, cost benefit uncertainty is usually where the battle is in code adoption at the local level. How do we overcome that with the rapid change in rates, mostly happening within the jurisdictions of regulatory commissions?
Well,
Go ahead, Ellen.
Within the performance-based compliance, you are able to use your local rate to determine the energy cost savings. So you are able to tailor it to your particular situation. I guess another thing we're trying to give better guidance by looking across all these different rates and coming up with some sort of a demand metric. And if you were to fall within this category, well, then this whole bunch of code requirements could be of interest to you. So to kind of layer on and make available code language across a wide variety of jurisdictions or jurisdictions with a wide variety of rates and make that language available.
One other thing I will mention that we're very proud of in Washington, or some of us are very proud of, we actually have a carbon metric in code. So it's actually not just cost, it's carbon impact. So that drives a very different discussion about what's effective, if you will.
Yeah, and that reminded me that some work being done in ASHRAE Standard 189.1, where they're updating their carbon metric, which is just an average carbon number based on current carbon, to use a future projection and also make it be based on an hourly value. So while that analysis is being done to look into that, it's also it's also a jurisdictional option. So there is that possibility to flexibility within codes that if you make it optional and if it's appropriate for just jurisdiction, they can adopt it.
Well, it looks like we are at time, so I want to be mindful of everyone's time here, and I want to thank Ellen and Mark again for discussing this timely and really important topic in the energy codes world. Just a quick plug again. This is a series of seminars that we have. So please go to the link that I added into the chat and sign up for a future seminar series. We have them every other week on Thursdays at this time. So again, I want to thank everybody for attending, and we will wrap it up here.
Thank you, Ian.
Thank you all.
Bye, everybody.
This has been the National Energy Codes Conference Seminar Series hosted by the U.S. Department of Energy. Join us for a number of other important topics in building energy codes, just like today's. Participate live in our upcoming events or listen to past events on demand through our energycodes.gov training portal. There you'll find other helpful tools and resources, from education and training materials to compliance tools like our ResCheck and ComCheck software, to the latest on state code updates, to analysis of energy code impacts from energy savings to cost effectiveness, and more. Check out energycodes.gov for those and a number of other technical assistance resources from DOE, Pacific Northwest National Lab, and others. From the DOE Building Energy Codes program, We hope you learned something new about energy codes and enjoyed today's session. Thanks for being part of the conversation, and we'll see you next time.